Hello all, my name is Supun Nakandala. In this talk, I will present you our system Nautilus, which is an optimized system for deep transfer learning over evolving training datasets. This is joint work with my PhD advisor, Professor Arun Kumar. Deep learning is revolutionizing many fields. For example, it's being heavily used in domains like e-commerce, web and social media, and interactive voice assistants. Furthermore, it's also being used in critical application domains, such as in autonomous vehicles and in healthcare. Inspired by these major successes, there is growing interest among data analytics practitioners to use deep learning for their analytics workloads. For example, imagine a use case where we have a data scientist who is working at a hospital and she has been asked to train a model to detect pneumonia conditions from chest X-ray images, which can be then used to prioritize the backlogs. She's aware about the recent advancements in deep learning and knows that she can train a deep learning model to achieve this goal. However, she realizes that in order to train such a model, she needs access to a large label chest X-ray image dataset, which a hospital does not have access to. In fact, all successful deep learning models have been trained on very large datasets, such as the ImageNet dataset, which has over 1 million labeled images. Similar to our use case, in many deep learning applications, initially, you don't have access to the large label datasets required to train these models. We also observed that in many of these applications, practitioners have to manually create the label dataset, which is tedious, time-consuming, and also resource-intensive. Luckily, there's a paradigm called transfer learning, which can be used to remedy these bottlenecks. With transfer learning, one will reuse a pre-trained deep learning model, such as the VGG16 model trained on the ImageNet dataset, in order to train a model for their given task, instead of training a model from scratch. And by doing so, they can significantly reduce the large label data requirement needed to train a deep learning model. However, even for transfer learning, the accuracy of the trained model will be highly sensitive to the chosen transfer learning scheme and also various other training configurations used during training. As a result, practitioners have to explore several different training configurations and pick the configuration that works best for their given task, which is also called model selection. We also observe that the current practice of executing these workloads incurs significant redundant computations that reduce user productivity and also system efficiency. So in this work, we formalize and optimize transfer learning workloads from a data management standpoint. Specifically, we cast training a deep learning model using transfer learning as a novel instance of a query and develop novel multi-query optimization inspired strategies for optimizing transfer learning workloads. The rest of my presentation today is organized as follows. First, I'll give some background on transfer learning and then present the different system optimizations performed by our system Nautilus. Finally, I'll present some experimental results using our system. Transfer learning leverages the fact that when you train a deep learning model on a large label dataset, the layers inside this model automatically learn to identify different features in the input data. For example, it has been shown that when you train a deep learning model on image data, the low-level layers automatically learn to identify different low-level features in the input images, such as edge patterns and color blobs. Mid-level layers automatically learn to identify mid-level features like specific texture patterns, and high-level layers automatically learn to identify high-level concepts like identifying different objects. And also notice that most of the features that the model has automatically learned to identify are generic enough to be directly reused in other similar settings. So with transfer learning in the picture, instead of training a model from scratch, you will start with a pre-trained deep learning model, such as VGG16 pre-trained on the ImageNet data, and use a significantly smaller labeled dataset of around at most few thousand data records, and train the model on this dataset. During this training process, a common practice is to freeze most of the lower layers of the model because the features extracted by these layers are generic enough so that they can be directly reused. And you will fine-tune parameters of only the remaining layers. However, the separation between which layers to be freezed and which layers to be fine-tuned is not straightforward. So in practice, practitioners explore several different layer freezing schemes. And in certain times, even freeze the entire model and explore several different feature combinations from the layers of the model, which is also called feature transfer. This is essentially a model selection step, and this type of fine-tuning and feature transfer is getting increasingly popular for both computer vision and natural language processing applications. Now, while transfer learning reduces the label data requirement, it does not completely eliminate it. We observe that for many practical applications, label data is generated often iteratively using techniques like active learning. So with active learning, you will use some kind of active learning sampler to sample a batch of unlabeled data items and present it to a domain expert to get the ground truth label, and then update the labeled dataset and use this updated labeled dataset to train a model and perform model selection to find the best model. Then you will use this model to sample the next batch of data items which are most informative to train this model, and repeat this process for several iterations such that you have labeled a sufficiently large labeled dataset that can be used to train a model with the required accuracy. Now, this type of workloads are often executed on low resource settings such as personal computers and workstations. Next, I'll talk about the system optimizations performed by our system Nautilus. Nautilus performs two different optimizations: materialization optimization and model fusion optimization. Now I'll start with the materialization optimization. Our materialization optimization is motivated by the observation that when you freeze lower level layers of a model, that part of the model essentially acts as a fixed feature extractor, and parameters of only the remaining layers will be changed during training. Deep learning training is an iterative process where at each iteration you have to read the entire data set. And this process is done for a couple of iterations, at least few dozens, which are also called epochs of training. So due to the iterative nature of the training, when you scan the data set for multiple iterations, you will start incurring redundant computations in the fixed or frozen model layers. When you explore several different layer freezing schemes, and these freezing schemes will correspond to different models, and you will start incurring redundant computations across all these models. Finally, when you repeat this process, whenever there is an update to the labeled dataset, you will start incurring redundant computations across data labeling cycles. Now, one solution for this problem is to pre-materialize large reuse frozen layers beforehand and read these features to train the remaining layers of the model. However, there are a couple of different problems with this approach. First, the size of the materialized features corresponding to the frozen layers for the entire dataset can be orders of magnitude larger than the size of the training data. So in low resource settings, it may be the case that you cannot simply materialize these features. Second, even if you can materialize these features and store them on disk, reading the features again and again from the disk to train the remaining model layers can incur significant I/O overheads that can impede the training performance. So the challenge here is to find an optimal materialization strategy that can conform to a given storage budget. And our solution for this problem is to cast this problem as a new instance of the classical materialized view selection problem in databases. And we use a mixed integer linear programming-based approach to find the optimal strategy. Our MILP-based solver takes in several inputs, including the model's graph structure, layer compute cost and output sizes, I/O and compute throughputs of the host system, and also a storage budget. And it will determine the optimal set of layers to be materialized. With the optimal set of layers to be materialized determined by our MILP solver, we will then rewrite the model graphs to reuse these features. And if there are any frozen layers that were not selected for materialization, we will recompute the features for these layers on the fly during training. And by doing so, we can reduce redundant computations across training epochs and also across different model configurations. With iterative data labeling, whenever there is an update to the label dataset, in addition to updating the label dataset, We will also incrementally update the intermediate features and use these features during model selection, and repeat this process for every data labeling cycle. And by doing so, we can reduce redundant computations across data labeling cycles. Next, I will talk about our model fusion optimization. Notice that even with our materialization optimization, we can still incur redundant computations in the frozen layers that were not selected for materialization. And also, reading the materialized features independently for training each model can incur redundant I/O reads. To overcome these bottlenecks, we propose our model fusion optimization. But the basic idea here is to fuse multiple models into a single larger model, where the trainable parts of each model will be a different branch in this larger model. And all these models will share a single backbone of frozen or materialized layers. During the model fusion, we ensure that runtime memory footprint of training this large model will not exhaust the runtime memory budget available in the host system, using the profiling information obtained from the source models. And by doing so, we can reduce redundant computations and I/O reads overheads across multiple model training within the same training epoch. As an overall summary of the different redundancies eliminated by our techniques, we see that our materialization optimization can eliminate all three types of computational redundancies, including the redundancies incurred when training a single model, redundancies incurred across multiple models, and also redundancies incurred across different data labeling cycles. And our model fusion optimization can reduce computational redundancies incurred across multiple model configurations and also I/O redundancies. More details about our optimizations can be found in our technical paper. Next, I'll present some experimental results using our system. As experimental workloads, I have selected three popular transfer learning workloads. FTR is a feature transfer-based transfer learning workload where the task is to identify named entities from text. For this, I'm using the popular NLP model BERT, and I'm going to explore several different feature transfer schemes. ATR is an adapter training-based transfer learning workload where the task again is named entity recognition. And for this, I'm going to train adapters for the BERT model for different layers configurations. Finally, FTU is a fine-tuning based transfer learning approach where the task is to detect malaria from cell images. And for this, I'm going to fine-tune different layers of the ResNet 50 model. For all these workloads, I'm going to explore two different training batch sizes and three different learning rates, which altogether ends up generating 24 different model configurations. As the data labeling setup, I'm going to label 500 records per iteration and repeat for 10 different data labeling cycles. I'm going to programmatically release the labels of the selected data items and evaluate the model selection runtime. All these workloads were executed on a single node machine. In terms of end-to-end experimental results, I'm going to explore and compare three different approaches. Current practice is the current dominant practice of training deep learning models with frozen layers as it is, and repeat this for each model and each layer freezing configuration. And it incurs the highest level of redundancies. MAT-all is a stronger baseline where we will pre-materialize features from the last reused frozen layer beforehand and read these features to train each model independently. And finally, Nautilus is our system which performs both our selective materialization optimization and also model fusion optimization. For current practice, depending on the workload, it can take different runtimes to execute this workload. And we observe that by using MAT-all, we can significantly reduce the runtime of these workloads with a higher speedup of 2.7x for the FTR workload. However, by using Nautilus, we were able to achieve even higher speedups with the higher speedup of 5.2x again for the FTR workload. We also compared the storage footprint of Nautilus and compared it against MAT-all and found that Nautilus can achieve faster performance with less storage footprint compared to MAT-all. As a summary of my today's presentation, I explained to you that transfer learning is a crucial paradigm for democratizing deep learning. However, the current practice of adapting transfer learning has significant system inefficiencies that impede human productivity. In this work, we reimagine transfer learning model selection as a multi-query optimization problem and develop two new optimizations, materialization and model fusion optimization, that can reduce transfer learning workload runtimes by up to 5x compared to the current practice. With that, I would like to conclude and take any questions. Thank you.